You've seen them before, these round shapes you used to hate taking the area of in geometry. A few days ago, I found myself thinking back to such times, and I asked myself, how many sides does a circle have? The answer can seem quite simple at first, but a whole new perspective can be achieved when really thinking about it. Take this image for example. How many sides do you see? There are many ways to view the question. Three reasonable answers exist, and I will cover each one to arrive at a definitive response. Riemann sums will be used to prove the possibility of infinite sides being an answer. This term is coined after Bernhard Riemann, a German mathematician. In essence, Riemann sums approximate the area under a curve. Take for instance the function y is equal to x plus 1. This function has the following graph. Now I know what you're thinking, these lines do not look straight at all. And you're completely right, this is not drawn to scale. But it'll serve for the purpose of this example. Now, what we're going to do is narrow the curve to the values between 1 and 3 in terms of x. Riemann sums facilitates our ability to estimate the space between 1 and 3, so what I'm shading in right now. The concept revolves around using rectangles so the area can be calculated. We will use two rectangles in this example. Moreover, three basic forms of Riemann sums exist, but we will use the left Riemann sum for simplicity's sake and the purposes of this video. We can use this formula to represent the Riemann sum and plug in the values, but it doesn't have to be that complicated. What we're going to do instead is draw in the two rectangles and take their areas for this estimation. So this is what they'll look like. Essentially, what we're going to calculate is this area here. The value for these Riemann sum would be as follows. So, as you can see, the first rectangle has a length of 2, and this is just simply taking the area. So it'd be 2 times 1, since that's the width. Now plus the other rectangle. So the other one has a length of 3 and times 1, which is the width. So all in all, it would be a value of 5. And that would be for the left Riemann sum. However, the area is a different story. And let's take it so that you can see. The area under this curve is rather simple. We could simply draw this rectangle here as well as this triangle above it. So as you can see here, this would be the function for the overall area. The area of the square plus the area of the triangle. So the square has an area of 2 times 2, and now the triangle has an area of 1/2 times the value of 2 times 2. So this would be 4, and this would be 2. So the overall area would equal 6. Now as you can see, the left Riemann sum is an estimation. It equals 5. However, the area under the complete curve is 6, and that's because when we drew these rectangles, we left out the space right here, since these are left Riemann sums. We can apply what we just learned to a circle. The function of a circle is as follows: x squared plus y squared is equal to z squared. Z simply represents the radius of the circle. Let's say z was 4, so the circle has a radius of 4. Therefore, 4 squared is 16. So let's use that function to represent our graph. If we were to solve for y to have a function a graph, then it would produce two results. These would be the two functions produced. The positive square root function simply represents the circle over the x-axis, while the negative square root represents the circle under the x-axis. Let's only work with the positive function, meaning the one over the x-axis. This produces a semicircle, but what applies to this half can be applied to the other. Now, the important thing about Riemann sums is that the more rectangles that are drawn, the more specific your calculation will be. Let's first draw 4 rectangles from values -4 to 4. As you can see, the semicircle, or what I tried to draw that is a semicircle, has a radius of 4. In terms of the 4 rectangles, this is what they'll look like. As you can see, some of the rectangles may go over the graph in these areas, and that is because this is a left Riemann sum, so we're taking it from the left value. And then of course, some rectangles underestimate the graph, as seen on this side. Let's do a Riemann sum for the 4 rectangles. So this would be the overall function for the different areas of the 4 rectangles. So as you can see, the first one has no area since it's 0 times 2. The second one, it stems up to the y value of 3.464, and of course it has a width of 2. Same thing for the last areas you can see here, since they kind of repeat. And then the one in the middle is 4 times 2. So overall, that's going to give an answer of about 21.856, and this is a rounded value. Now, in terms of the area, this one would be more complicated to take. You could use calculator integration, several methods to arrive at an answer. However, I'll make it easier for us and give us the area, which would be 25.133. So as you can see, there is a great difference between the two values, 21 and 25, somewhat of around 4. Now, to prove that as we add more rectangles, the value is going to approximate this area, so the actual value under that semicircle, let's use 8 rectangles instead. This is what using 8 rectangles would look like, and this would be the function now. So as you can see, now the width decreased to 1. That's why I put for the first value 0 times 1. However, I didn't rewrite the 1 every time because this is negligible, much like the parentheses, but for some reason I wrote them. All in all, this would produce a value of 23.966. This is much closer to the area. As we said previously, it was about 25.133. So if you continue to add in more rectangles, this value, the left Riemann sum, will come closer and closer to the area under the semicircle. The same applies for the other half of the circle under the x-axis. Now, what exactly is the point of all these numbers? Well, as I mentioned previously, taking the sum of more rectangles will give you a more accurate answer, meaning that it will be closer to the true value of the area under the curve. This means it will take an infinite amount of rectangles to account for the area inside a circle. Overall, this implies that a circle has infinite sides as more and more rectangles are placed within it. With all this information, we have our first theory. A circle has infinite sides. You will begin to notice that each theory requires different definitions of the word side. The first perspective has you view them as extreme points, meaning those points that are furthest away from the middle of a shape. Every point on a circle is an extreme point, so there are an infinite amount. We can also expand on this view in a different matter. If we begin with a square, as shown here, well, it's kind of more of a rectangle, but it's still 4 sides. So if we add one more side, another extreme point, it'll become a pentagon. We add another one, it'll become a hexagon. As you can see, you add more and more sides, the shapes become more and more round. If we keep increasing these extreme points, the shape becomes more circular in nature. This can be another view explaining why a circle can be said to have an infinite amount of sides. Adding an infinite amount of extreme points will eventually make you arrive at a circle. Now, that's been theory 1. Let's switch over to theory 2. Now, you're going to hate me for this, but theory 2 does depend on less math. Moreover, the definition of side here will change to intersecting line segments, so where two lines meet. As we mentioned previously, increasing to an infinite amount of extreme points can create a circle. However, this means that no converging line segments exist on a circle. If a circle lacks both a measurement of length because there are no oblique lines drawn, this is in a square for example, or a pentagon, it has no length. That's why we use different measurements to calculate its area. So because a circle lacks both measurements of length and corners, it can be said to have 0 sides. 0 and infinity make for a paradox, but the two concepts are more similar than we realize. I would like to leave this idea for a future video, but it can be said that those who view a circle as having infinite sides or 0 sides are not that far off from one another. Finally, theory 3. This one requires a completely different perspective from the two we have already discussed. A circle differs greatly from a sphere, as the former is a 2D shape, the latter is a 3D shape. This means, unlike a sphere, a circle has one face. Arriving at the conclusion that a circle has one side means that you view a side simply as the face of a shape. This view is not incorrect since it changes the definition of what a side means. However, viewing the discussion by this definition means that other shapes, such as a square, for example, or a rectangle, they would also only have one side. So there'd be no way to distinguish shapes from one another because a circle would have one face, and so would this square or rectangle. All in all, how many sides a circle has comes down to what your definition of sides is. How many sides do you think a circle has? Let me know down in the comments below.